Okay, let's unpack what we're looking at today. For the last couple of years, the whole conversation around AI has really been dominated by the software, hasn't it?
Oh, absolutely. The chatbots, image generators, all the large language models.
Exactly, the stuff you can see and touch. But behind all that flash, there's been this incredibly aggressive arms race for the actual physical hardware that runs
The
everything.
silent arms race, yeah.
And for a long time, the story was simple. It was Nvidia, they had the GPUs, they had CUDA, their software, and they basically had a monopoly on high-performance compute. But that story, it's changing.
It's changing right now. And what we're looking at is the centerpiece of that challenge, Google's newest project, codenamed Ironwood,
The seventh generation TPU.
TPU v7.
That's the one. And it's really critical to understand this isn't just a small step up. It is a strategic pivot for the entire AI landscape.
A pivot how? Well, for a decade, the whole hardware war was about training. The really expensive part of building the AI brain in the first place. Ironwood. Ironwood flips the script. It's all about aggressive optimization for inference.
So not building the brain, but actually using it.
Exactly. Using it to serve answers, predictions at a massive global scale. This is Google's big proprietary swing at breaking the crazy cost barriers of running something like Gemini for billions of people.
So why does this matter to you listening right now? I mean, if you're running an AI app, or maybe you're the one who has to approve the cloud compute budget every month,
Yeah.
you really need to get this shift.
Because that monopoly is starting to crack.
And it's specialization, like what we're seeing with Ironwood, that's really applying the pressure. So let's start there with this age of inference you mentioned.
That's absolutely the right way to frame it. The first wave of AI was all about, can we do it? Can we build a model with 1 trillion parameters?
And we found out the answer is yes.
Yes. But now we're dealing with the economic reality. Running these huge models all day, every day.
Yeah.
It is ruinously expensive. Every token generated costs real money.
It's like the operational costs are just bleeding out. So the hardware has to be designed to stop that bleeding.
Precisely. And that's where something called a domain-specific architecture, a DSA, comes in. A GPU, a general-purpose GPU, has to do everything, graphics, crypto mining, you name it.
Right.
But the TPU has always been an ASIC, an application-specific integrated circuit. It does one thing, and one thing only, really, really well.
Matrix multiplication, the heart of deep learning.
And Google is claiming, with the headline figure,
4x better performance per chip compared to the last generation.
Right.
I mean, that is an enormous leap. To get there, they must have just completely ripped up the blueprints for the inside of the chip.
They did. That jump comes from a massive overhaul of the matrix multiply units, the MXUs. The whole philosophy is different. For inference, you need maximum throughput and, crucially, minimal latency.
Talk about that latency. Why is it so important for inference?
Think about it in practice. You're serving a model like Gemini to a user. If that model takes 3 seconds to reply,
The user's gone. They've closed the tab.
the engagement is lost. Ironwood is the hardware answer to that specific problem. It's not about training the model faster anymore. It's about making it reply instantly.
And that gets us to arithmetic precision. You said it leans on lower precision, like an 88. Now, for people who follow hardware, that sounds wrong. You usually want more precision, right?
Yeah.
Why is less better here?
That is the perfect question, and it's the key difference between general and specialized hardware. When you train a model, you need high-precision 16-bit, 32-bit floats because you're making tiny, tiny adjustments to the weights.
You need to be delicate.
Exactly.
Right.
But once it's trained and you're just running it, you don't need that granularity. The model's robust. 8-bit math is perfectly fine. And by making that switch, you get these massive efficiency gains. Lower precision numbers are smaller. They need less complex circuits. This lets Google cram way more of these compute units onto the same piece of silicon, which directly lowers the power use and the cost for every token you generate.
So they're trading that do-everything versatility for raw, cost-effective speed in production. Okay, that makes sense. But here's the pushback I always hear. A single fast chip doesn't matter anymore. The real bottleneck is communication.
You've hit on it. That is the single biggest problem in modern AI. You can have the fastest chip in the world, but if it can't talk to its neighbors fast enough, the whole system grinds to a halt.
So let's talk about the acronym that defines this war. ICI, the Interconnect. What did Google do here?
They didn't just break the speed limit, they absolutely shattered it. Ironwood has a 9.6 terabits per second ICI.
Wait, say that again?
9.6 terabits per second. And
Yeah.
to put that in perspective, your fast home internet is maybe 1 gigabit. This is almost 10,000 times faster between each chip.
I can't even picture that. It's like transferring an entire hard drive in a blink.
Less than a blink. And the practical result of that speed is synchronous performance. This isn't your normal chatty Ethernet with all its overhead. This is a direct, dedicated mesh network. Latency between chips basically disappears.
And that lets them build, what do they call it? The Superpod?
The Superpod. This speed lets Google link 9,216 of these chips together into one unified system. And with near zero latency, you can do true model parallelism.
Meaning you can split one giant neural network across all 9,000 chips.
And they act like one single, massive, coherent brain, not a bunch of separate computers passing notes.
So when you rent a slice of Ironwood in the cloud, you're not just renting a virtual machine, you're renting a piece of a supercomputer. That whole distinction just vanishes.
It does.
But I have to bring up the big skepticism point here. This amazing interconnect only helps if people can actually use it, right? Google Software XLA, JAX, it's historically been harder for developers to switch to, especially if they're all in on Nvidia's CEA.
That is the multi-billion-dollar question.
So how do you convince them?
You don't convince them with convenience. You convince them with raw economics. If your AI costs, say, $100 million a year to run, and switching to Ironwood saves you $30 million, well, that financial pressure starts to outweigh the pain of porting your code.
So the target isn't the research lab, it's the huge companies where every fraction of a cent on the compute bill matters.
Exactly. The hyperscalers.
Which frames this competition perfectly. This isn't an apples-to-apples fight between Ironwood and, say, Nvidia's new Blackwell GPU.
Not at all. It's more like comparing a Formula One car to a high-performance rally car.
I like that. Explain.
The TPU is the Formula One car. It's built for one very specific track, one perfect task, and it's unbeatable at it. The GPU is the rally car. It's amazingly versatile. It can handle any terrain, but it has to carry that extra weight, that extra complexity.
Let's talk about memory. LLMs are famously memory-bound. They're always waiting on data. In that Superpod setup, Ironwood has 1.77 petabytes of shared HBM, high bandwidth memory. Why is the shared part so important?
That's where the scale of this system just shines. A huge language model has massive weights. If those weights don't fit into the memory of one chip, you're constantly swapping data back and forth over slower connections.
Which creates bottlenecks.
Huge bottlenecks. By pooling 1.77 petabytes of this super fast HBM across that synchronous mesh, Google basically ensures that even the biggest models you can imagine can live entirely in high-speed memory. It just kills that data transfer problem.
Which brings us back to that core debate, versatility versus specialization.
And the software mode. Nvidia's strength is CUD. It's mature, it's flexible, it runs everything. Nvidia has to build a chip that works for everyone, for every framework.
And that creates a silicon tax, as you called it.
It does. A big chunk of their silicon has to be dedicated to things that a pure inference engine like Ironwood just doesn't need. General purpose logic, graphics, pipelines, Ironwood skips all that. It's an ASIC running XLA, tuned for Gemini. It avoids the tax, and that translates directly into better power efficiency.
Okay, so to sum up the showdown, if you're a researcher trying out 50 new ideas, you stick with Nvidia. CDA gives you that flexibility.
It's the safe bet.
But if you're deploying a known model, like a transformer, at a massive scale and you're paying that electric bill, Ironwood is built to be the better economic choice.
It's the economic engine.
Now let's get to the meta story here, which I think is just fascinating. We're hearing that Ironwood wasn't designed just by humans. It was designed in part by Google's own AI, AlphaChip.
This is where the story gets really interesting. It just loops back on itself. AlphaChip uses deep reinforcement learning, the same AI that mastered Go to do chip floor planning.
And floor planning is what exactly?
It's basically a game of Tetris. With billions of transistors. He has to place all the logic, all the memory on the silicon to make the wires as short as possible and reduce power use. For a human, it's an impossibly complex puzzle.
But for AlphaChip, it's a game it can learn to win.
Precisely. It learns through trial and error what placements lead to better outcomes, like less power consumption. It's pre-trained on tons of old chip design, so it gets really good, really fast. Google says it generates superhuman layouts.
So wait, the AI, which runs on TPUs,
is designing a better TPU.
Which then runs the AI faster.
So it can design an even better TPU next time. It's an acceleration loop, a recursive feedback system.
And that's a proprietary advantage nobody else has. They're not just using standard design tools. They have an AI that can explore the design space in ways a human just couldn't.
And for Ironwood, that directly resulted in shorter wire lengths and lower power consumption. It's a real measurable benefit.
All this technical power, though, brings us to the business model, because there's a huge catch here, isn't there? You can't just go out and buy an Ironwood card.
You cannot. That's the ultimate constraint. It is exclusively available through Google Cloud. It's hardware as a service.
And let's contrast that with buying Nvidia hardware. If you're a startup, you need millions of dollars in upfront CapEx, in capital expenditure. And then you have to wait, what, a year sometimes?
Up to 52 weeks, yeah. The lead times are crazy. You're spending millions today on a bet that you'll need that capacity a year from now. It's a huge risk.
But with Ironwood, it's OpEx, operational expenditure.
You just need a credit card and an API call. You pay for what you use. That financial flexibility is, for many of these big customers, more important than the raw specs.
And even if the hourly rate for Ironwood is high at first, those 4x efficiency gains mean your actual price per token, your effective cost, should drop significantly.
That's Google's masterstroke. They control the whole stack, the chip, the compiler, the data center cooling, the cloud service. They don't need to make a profit selling the chip.
They make the profit when you use it.
Which lets them offer a price-to-performance ratio that's just very, very hard to compete with if you're only selling hardware.
Okay, let's wrap this up. We have to ask the big question everyone's debating online. Is Ironwood an Nvidia killer?
No, absolutely not. It's not an Nvidia killer. Nvidia's dominance in research, in gaming, in places that need that ultimate flexibility, that's safe. You can't just take any PyTorch model and run it seamlessly on Ironwood like you can on CUDA.
But it's more than just another competitor. It feels like a warning shot.
A definitive warning shot. It proves that at the highest scale, vertical integration wins. If your model costs $100 million a year to run, and Ironwood's efficiency can cut that bill to $70 million, the argument about platform flexibility starts to sound a lot less important.
The economics just take over.
They do.
So the implication is that the AI hardware world is splitting in two. You'll have versatile GPUs for development, and then these massive purpose-built AI supercomputers like Ironwood for the real heavy lifting in production.
Ironwood is the proof of that transition. The whole focus is shifting away from just raw model size to the economics of deployment, the efficiency, the speed.
Which leaves us with a final thought. We now have to seriously consider the implications of a world where the hardware that runs our most advanced intelligence is increasingly being designed by that intelligence itself.
With things like AlphaChip, yeah. The hardware wars are really just getting started.